Okay, so for our final topic in the area of scale-free phenomena, we're going to talk about evolutionary processes. So here we're concerned with systems where there is evolution, change over time, and that seems to involve periods of relative stability interspersed with periods of rapid change, transformative periods. And this is known as punctuated equilibrium. So the system remains in equilibrium for a while, but then that is occasionally punctuated with periods of breakdown and kind of chaos and disorder, and then out of that a new equilibrium emerges. And we see that in biological evolution. So for example, with the dinosaurs, the world was dominated by the dinosaurs, and they formed an interlocking ecosystem that was relatively stable for millions of years. But then all those dinosaurs went extinct, and there was a rapid evolution of new species and the rise of the mammals, which then grew up and formed a new biosphere, a new set of species that were in relative equilibrium with each other and relatively stable. And we've seen from the idea of sampiles and self-organized criticality that we don't necessarily need to explain that extinction of the dinosaurs in terms of a comet from outer space. It could be that it's just a property of the system itself, that as species are going extinct all the time, occasionally one species going extinct can trigger a chain reaction that causes the whole network of interacting species to collapse and disappear. It is a property of the system itself. And we see also this kind of punctuated equilibrium in history and society, which is the reason we're studying it. So, for example, in society, we see something like the French Revolution. So before the French Revolution, you had a set of institutions that stabilized French society, like the monarchy, the aristocracy, the church. These formed a sort of interacting system that was relatively stable for centuries. But then in the French Revolution, all that disappeared. It was all swept away. Everything, the society was broken down, and you went through a period of chaos. And then out of that emerged a new set of social institutions that then formed the basis of French society after, going forward from that until the next breakdown. And you also see this kind of punctuated equilibrium in economic affairs, for example, with the Industrial Revolution. So before the Industrial Revolution, people made their living by working on the land, and the way of life had persisted, for centuries. But then with the Industrial Revolution, with its steam power and its factories and its globe-spanning commercial networks, there was a rapid transformation in the way people lived and made their living. They left the fields and went into the factories. So that was a period of rapid transformation. But then out of that came a new, relatively stable way of life, of economic life, and of how people made their living, that has remained in place, to the present day, or at least till recent times. Punctuated equilibrium seems to be a property of these complex systems, and certainly of social and historical systems which we're studying. And as I say, the point is that to explain these periods of rapid transformation, we don't necessarily need to introduce external factors. We don't need to introduce comets from outer space. It's possibly just a property that the whole way the system behaves, it produces these breakdowns of its own accord. And it's important to understand the general workings of the system, because those periods of breakdown are relevant to how the system works. They're not just some acts of God that we can explain by specific causes. some Austrian researchers have developed a computational model of such processes that generates the kind of behavior we're looking for of periods of stability and periodic collapses and periods of transformation. And they call it the coevolving combinatorial critical model, the CCC model. And as we go through it, we'll understand, why it's called that. So this model is based on the idea of an autocatalytic set. Autocatalytic set. And this is an idea that really comes from biochemistry. So in the cell, the living cell, it requires certain chemicals to function, and those chemicals are produced in the cell through chemical reactions involving catalysts. So the cell needs the catalysts to produce the other chemicals that it needs. And in the cell, you have all the chemicals and all the catalysts needed to produce all the chemical reactions that generate those chemicals, including the catalysts themselves. So the cell is autocatalytic. It is self-sustaining. It has everything it needs. It can catalyze every reaction that it needs within the cell, and produce those catalysts itself. So let's suppose that if we say we've got here a cell, we might have a chemical which I'll call A, which is needed by the cell. And let's say that the chemical A, to produce that, requires a chemical, its catalyst, B. Well, that is not autocatalytic, because yes, we can produce A, but we need B, and we need to get B from outside the cell. So it's not self-sustaining, it's not autocatalytic. But let's say we have another chemical C that produces B. Well, this is still not autocatalytic. So with C we can now produce B, which then allows us to produce A. But we need C, so we still got to get C from outside. But then suppose that A happens to be the catalyst that produces C. Now it is self-sustaining. So C produces B, which produces A, which produces C. So we got everything we need. Now obviously this is, a ludicrously simple example, and the reality in the cell is hundreds or thousands of different chemicals that form complicated networks of dependency. But we can just imagine this as an example of an autocatalytic set with three elements. And so yes, we see this in biochemistry, but we also see it in history and society. So, for example, in the economy, we could say that farmers need tractors, tractor manufacturers, to provide them with the tractors to work the fields. And tractor manufacturers need steel producers to, produce the steel that makes the bodywork of the tractors. And steel producers need food from the farmers. So the economy is autocatalytic. It sustains itself. Or we could say the same with technologies, that they're connected in networks of dependencies. So, a smartphone requires all sorts of inputs of smart glass screens and computer chips and microwave technology and so on. And so you've got networks and those in turn depend on other things. And so you've got these ramifying networks. And ultimately it's autocatalytic because all these technologies sustain each other. So, you know, we could say, for example, that for metalworking, the technology of metalworking, you need the technology of bellows to drive the, you know, power the furnaces that create the high temperatures for metalworking. And those bellows, you know, are made of wooden frames. So to produce bellows, you need the technology of woodworking that can create these bellows. But for woodworking, you need metal tools. So woodworking relies on the technology of metalworking. So you've got, again, an autocatalytic set. So that is why we're interested in autocatalytic set. And we're also interested in this punctuated equilibrium that we seem to see in these networks of social institutions or technologies or economic functions. And that's so the coevolving combinatorial critical model starts with this idea of an autocatalytic set, and then you know, it has many more connections than these. And in the computer simulation, there's a constant process of mutation. So it might be that one of the elements, which could represent molecules, or it could represent technologies, or it could represent social institutions. It's just arbitrary in the computer what it represents. But one of these elements can maybe mutate so that it no longer catalyzes A, but it catalyzes something else. And or we could delete elements, or we could add them, and, you know, add a new element that powers some other reaction. And with these mutations, if you've got a whole set of molecules, let's say, or technologies that are interacting, these mutations most of the time don't disrupt the stability of that network. It's kind of, you know, interlocking enough because maybe there are some redundant dependencies here. You know, even if B disappears, there's E or Z that produces A. But then if B goes and then Z goes, then you've got a problem. So most of the time those mutations can be absorbed, but occasionally the mutation sets off a chain reaction that causes the whole thing to collapse. If you take away B, you take away A, which then takes away C, and so on. It ramifies through, and so the whole thing collapses in this computer model. And then but the mutations keep happening, and you know, linking up with each other. And after a while, you just by random chance hit on a new set of molecules or what technologies, whatever they represent, that do interlock and become autocatalytic again and self-sustaining, and then you get back to a new level of stability. So it's a little bit like the Sandpar model in a sense that you know, there's a constant a process of mutation going on, like there's a constant drip of sand onto the sandpile, and that that can set off avalanches. But in this case, what it sets off is a complete collapse of the system, whereas in the sandpile it just sets off avalanches of different sizes. And what you then find is that I'll plot it here. This is time along here. If we have periods of stability, so I'll just, this axis doesn't really mean very much. I'm just distinguishing between periods of stability and periods of change, or maybe I should say disorder. So in the periods of stability, you've got an autocatalytic network. In periods of disorder, which I'll represent sort of like that, you've got no autocatalytic network. You've just got a set of random elements that are laws unto themselves. And so once this mutation process has set off this avalanche causing the collapse of the autocatalytic set, you're in a state of disorder, but then you eventually find a new autocatalytic set and you're back to a state of stability. But then that itself may break down. And then you're in a new period of disorder, and then you recover a new autocatalytic set and you're in a period of stability, and then again you break down, and so on. And the point is that you then get, or you find that you get power law statistics, fat tail statistics in either the durations of these breakdowns or in the durations of the periods of stability, the intervals between the breakdowns. So you've got a power law n of s proportional to s to the minus alpha, where s is either the duration of the period of disorder or the duration of the period of stability, whichever it is. But you can generate with this computer model these periods of breakdown that have that fat tail power law type property. So having this power law fat tail property, it suggests it's like a critical system, because it's in critical systems that we see the potential to generate power law statistics. For example, the avalanches in the sand pile model. So here the network evolves into a critical state where this constant rate of mutation can trigger periods of disorder of different durations that obey power law statistics. So that is why it is coevolving. So you've got sets of elements that are always mutating, and they affect the rest of the network. So the whole thing is evolving as the individual items mutate. That eventually causes mutations in the overall network. It's combinatorial because you've got these combinations of interactions in the network, and it's critical because of this fat tail property of the statistics, this power law property of the statistics. I should say that whether this is actually a good model of technological evolution, I'm not so sure, because what you might say is, say we had, before the invention of the motor car, people got around by horse transport. There was a whole technological ecosystem based on the horse, and there were horse breeders and horse dealers who sold the horses to the coaching companies, and then there were coaching inns that had stables for the horses, and the hay suppliers to the coaching inns, and there were the people who scraped the manure off the roads and sold it to the farmers, and so on. So there was a whole set of economic functions built around the institution of the horse, the technology, if you like, of the horse. But then when the motor car came in, it swept away all that. And eventually there grew up a new ecosystem, a new technological ecosystem based around the motor car, with petrol stations and mechanics garages and so on. So with this model, the co-evolving combinatorial model, you might say, oh well, it's that's an example of that. It was the evolution, the mutation from the horse to the motor car affected the whole economic network. But I'm not sure it was really quite like that. That there was, when the motor car was invented, that there was a complete collapse of the technological ecosystem, and then and that also that the motor car, the change from horse to motor car, was kind of a random mutation that then caused the whole collapse of all the the entire economy, and then everything was in chaos for a while, and then it rebuilt from that. There was more of a sort of gentle switch over, and the motor car coming in produced those changes that caused the technologies and economic functions to adapt to the new reality. So yes, I'm not so sure it's really stable. Then the motor car comes along, we collapse into complete chaos and disorder. We then remain there for some period, and then we climb back out of it. I'm not sure that's really a very good description of how the technology of the motor car came in. Which doesn't mean this, there's a problem with this model. The model is what it is, and it's certainly a useful tool for thought. But as with most of our models, it's not the be all and end all, the answer to everything. It's it describes some processes that may be involved and help us think about what's going on, but it's not in itself the solution to anything.